All right, so today we are going to be considering the problem statement that states P of n is equal to n times n plus 1 times n plus 5 is a multiple of 3 where n is an element of the set of all natural numbers. And to prove this, we are going to be using principle of mathematical induction. Our first step is to show that P of n is a multiple of 3 when n equals 1. So here we have P of 1 equals 1 times 1 plus 1 times 1 plus 5 is equal to 12. And that can be simplified into 4 times 3, meaning P of 1 is a multiple of 3. Our next step is to assume that P of k is true, where k is a positive integer. P of k equals k times k plus 1 times k plus 5 is equal to 3 times m, where m is an element of the set of all integers. Next is to prove that P of k plus 1 is also a multiple of 3. And here we have, since P of k is true, we have that k times k plus 1 times k plus 5 is equal to 3m. And that can be simplified into k cubed plus 6k squared plus 5k is equal to 3m. And so now for P of k plus 1, we have k plus 1 times k plus 2 times k plus 6 is equal to k cubed plus 9k squared plus 20k plus 12. And that can be rewritten as k cubed plus 6k squared plus 5k plus 3k squared plus 15k plus 12. That means that k plus 1 times k plus 2 times k plus 6 is going to equal this right here. And so as you can see, I highlighted k cubed plus 6k squared plus 5k because we saw that earlier for P of k, where k cubed plus 6k squared plus 5k is actually equal to 3m. So I went ahead and rewrote the problem as 3m times 3k squared plus 15k plus 12. I went ahead and factored the 3 out, so now we have 3 times m plus k squared plus 5k plus 4. And so therefore, P of k plus 1 equals k plus 1 times k plus 2 times k plus 6 is a multiple of 3, meaning the statement P of n is true for n is an element of the natural numbers, and it is proven using principle of mathematical induction. Thank you very much. Quod erat demonstratum.
Prove by direct proof. The sum of an even number and an odd number is odd. So we're going to assume that a is an even integer. Therefore, a is equal to 2 times m, where m is an element of the set of integers. And b is an odd integer, so b is equal to 2n plus 1, where n is an element of the set of integers. And then now we're going to have a plus b, and over here we're going to have 2m plus 2n plus 1. So factoring this out gives us 2m plus 2n plus 1. We can group these together. And then here, m plus n can be substituted out for k, therefore giving us 2k plus 1. Therefore, by direct proof, the sum of an even number and an odd number is odd.
Proof by cases. Prove that if x is a real number such that quantity x squared minus 1 all over quantity x plus 2 is greater than 0, then x is greater than 1, or negative 2 is less than x and less than negative 1. By proving this, you first want to expand your numerator into quantity x minus 1, quantity x plus 1, all over x plus 2 is greater than 0, where x minus 1, x plus 2, and x plus 1, all combined, are greater than 0. By using cases, in case 1, x plus 1 is greater than 0, x minus 1 is greater than 0, x plus 2 is greater than 0, and in this case, x is greater than negative 1, x is greater than 1, x is greater than negative 2, which implies that x is greater than 1. In case 2, x plus 1 is greater than 0, x minus 1 is less than 0, and x plus 2 is less than 0. In this case, x is greater than negative 1, x is less than 1, and x is less than negative 2, and no x solves the inequality. In case 3, x plus 1 is less than 0, x minus 1 is greater than 0 and x plus 2 is less than 0. In this case, x is less than negative 1, x is greater than 1, and x is less than negative 2, which again, no x solves the inequalities. And in case 4, x plus 1 is less than 0, x minus 1 is less than 0, and x plus 2 is greater than 0. In this case, x is less than negative 1, x is less than 1, and x is greater than negative 2. And the solution we have then is negative 2 is less than x and less than negative 1. Therefore, either case 1, where it proves x is greater than 1, or case 4, where it proves negative 2 is less than x and less than negative 1, signifying that the proof statements are true by cases.